Okay, so on page 791, problem 49 reads, a spherical conductor has a radius of 14 centimeters and a charge of 26 microcoulombs. Calculate the electric field and the electric potential at R equals 10 centimeters. At A, R equals 10 centimeters, B, R equals 20 centimeters, and C, R equals 14 centimeters from the center. So I've already set it up here. Here's our spherical conductor. We know what the charge is. We're given the radius is 14 centimeters. And it's a conductor, or a metal, which means all the charge is on the surface. Okay? Now, part A. Let's do part A. We want to know what is the electric field and the voltage at these different places. And part A is the most interesting one. This is really important. I'd like everyone to pay attention to this. Because, okay, E is at R equals 10 centimeters, it's pretty easy. If I put a Gaussian surface this is 14 centimeters, so 10 would be right around in here, inside the sphere. And you go, oh, there is no charge inside my Gaussian surface. And it's a conducting sphere anyway. So you can't have an electric field in there. So you can say, well, let's just go ahead and say E dot dA equals Q enclosed over epsilon naught. And you say, well, there is no charge. This is 0. And since the area can't be 0, the area isn't 0, the electric field has to be 0. So therefore, the electric field at any point in there is equal to 0. Now what about the voltage though? And here's the part that really throws people off when they confuse electric field for voltage. The voltage in there is not equal to 0. Because here's what voltage is for a charge distribution like this. Suppose I'm a little test charge way out here by infinity. So here's my little test charge, short and stout, and I'm going to push it against the field created by all these charges around here, and I'm going to add up how much work it takes me to do and then divide that work by the charge on my test charge, and that's my voltage. So I'm infinitely far away, I'm at 0 voltage. And I have to do work against the field to bring it here, and then bring it here, and then bring it here, and bring it here, and bring it here, and bring it here, all the way to here. And I'm adding up all that work I'm doing and dividing it by my test charge to get my voltage. And then I get inside. And once I'm inside that sphere, there's no more electric field to do work against. So I'm not changing my voltage anymore. Once I get inside, once I take this test charge and move it and put it inside here, I'm no longer adding or taking away from my voltage. My voltage is constant. So it's not 0. It's the voltage I get when I'm on the inside of this conductor is the accumulated work that it took me to go from infinity all the way to the surface. So the voltage is going to be equal to the work it took me per unit charge to get from infinity to that surface. Well, it looks just like a point charge, and so we're just going to call that KQ over R, where R is now the radius of this sphere. And so this is going to be 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. And then I'm going to multiply that by the charge, 26 microcoulombs. And then I divide that by 0.14 meters. And the question that somebody asked me is, if we're at 10 centimeters from the center, why are we dividing it by 0.14 meters? It's because at 0.14 meters is when once I get inside 0.14 meters, it doesn't matter anymore. I'm not adding any more voltage because there's no electric field inside there to do work against. So this is the radius I want to use. to figure out what that maximum voltage is. And so you plug all those values in. And according to the book, when you do that, let's see, 49, you get 1.67 times 10 to the 6 volts, or 1.67 megavolts. Okay, so there's my answer for part A. The electric field is 0. The voltage V is equal to 1.67 megavolts. Now, by the way, I am, for the sake of time, I'm cheating a little bit, right? I'm saying this is what it is, and there's my answer, and I look it up in the back of the book. That's really bad to do. Because what if you did something wrong, and then you would say, oh, this something wrong is equal to the right answer. I know this is right, so you got to check it. You got to do the work on the calculator and check it. So don't do as I do as I say. Typical hypocrisy. All right. Now for part B, R equals 20 centimeters. So now we're out here somewhere. And if I'm out here, that means all the charge is contained by my Gaussian surface. And so E is just going to be equal to KQ over R squared. So this is, again, 8.99 times 10 to the 9. Times my charge. And now I'm going to divide it by 0.20 meters, and you have to square that. And I'll let you look up the answer for that. Now the voltage, now since we're outside, it's just KQ over R. Right, it looks just like a point charge. When you're outside here, the electric field out here behaves like a point charge, and so the voltage behaves like there's a point charge there, and so you just plug the values in there and you'll get it. Where again, R here is the 0.2. You're just not squaring it. And then for part C, I'm going to leave that to you as well, because you're just doing the same thing. You're going, well, we've already done the work for the voltage. It's just KQ over R, where R is 0.14. So you'll get 1.67 megavolts. And then for the electric field, it's just KQ over R squared. So I guess you could just take this 1.67, divide it by 0.14, and you'll get the answer for the electric field. And that's the electric field just infinitesimally off the surface of the conductor. If you go infinitesimally into the conductor, the electric field is 0. And it's that quick. It just goes from that maximum value to 0 in 1 atom width. Okay? So anyway, that's how you do number 49.